Yeah, so this is gonna be empirical part. So how to choose the correct model and how to estimate the properties of that model. So this is gonna be something similar to what we have done in statistics and probability. So in probability, we outlined some theoretical concepts, random variables, characteristics, moments, expected values, so covariances, variances, and so on. And then in statistics, we discussed how to fit all of these into the data. So you observe some data points, collect some numbers, and then based on these numbers you are trying to figure out, so well, which model is the best for for modeling the processes that kind of like that are in the ground of the data. Then we will talk about some specifics. So here are the linear models, and then we will switch to something which is called non-stationary time series models, non-linear time series models. And if we have time, and if we are lucky enough, we will also talk about multivariate time series models. So when several variables are somehow connected. So this is our plan for the next 3 Saturdays, doing 2 lectures every Saturday. I hope we will manage doing this. So again, 2 lectures are gonna be mostly like mathematically grounded, and then we will start doing some empirical part with Python, data, estimations, forecasts, and all the related things. So what we're talking about, time series data are data collected on the same observational unit at multiple time periods. So we have seen in the first lecture of this course panel data. So panel data was a cross-sectional data when you have a lot of units and then you observe each unit over time. So now we observe only one unit over multiple periods of time. For example, aggregate consumption and GDP for a country. We take a particular country, we set the range of dates, for example, quarters, 80 observations. And then at every quarter, we observe and register the value of aggregate consumption, or GDP, or something else, some other macroeconomic variable, unemployment rate, inflation, imports, exports, whatever. Currency exchange rates, China yuan to dollar, dollar to ruble, euro to ruble, whatever. So we also have a date range, for example, 365 observations per year. Well, usually less, because we are talking about business days in this case. Usually there are like 260 days probably. And at every day we register like average rate or the rate at the end of the date or something like the official rate from the central bank or something like that. It might be something like social demographic characteristics like cigarette consumption per capita for a country. Again, so you can collect these for, I don't know, monthly, annually, quarterly, whatever. Daily returns of Gazprom stock. So everything that develops over time and can be kind of tracked over time is a time series. So here are some graphical examples taken from the textbook that we are using. So unemployment rate in the US from 1960, so it behaves something like this. Exchange rate of US dollar to British pound over the 52 years. And here is the logarithm of index of industrial production in Japan. And here is the change in daily values of stock price index, like Wilshire 5000. So 5000 stocks are somehow averaged, and then we have this percentage change, so return. So we see the time series, so probably you can catch from this picture that the time series are different in nature. So some of them are kind of fluctuating around the mean. So here is 0, and your time series is kind of going there and back around 0. Some of them are showing kind of trend. So they are trendy, so they tend to increase over time with some deviations from this trend. Some of them are kind of like peculiar in the shape. So we see that there are like long periods of upward increases and then downward development. And over this development, it also behaves somehow kind of randomly. And here, for example, when we are talking about exchange rate, so we see that there are different, even different segments of the development. So for example, this part is naturally different from this part. So there was something special here, which probably ceased to be in place like here. So something new started here, and maybe something new also here. So we see that time series can be divided into several parts. So why are we talking about this? Well, first of all, that we have to, right, to pass the exam. I'm joking. So, like practically, why are we interested in time series? We in practical work, when we work with analytics, when we work with some kind of like data science, machine learning, and all the related things, so we always encounter something like time series. First, and the most important task in the time series models is to develop forecasting models. So we want to predict something in the future. Since this is the value developing over time, we really want to kind of foresee the future with some knowledge from the past. So for example, what will the rate of inflation be next year? What will the stock price be the next year? And something like that. So what is going to be in the future? So people are always trying to predict something in the future. They want to see what's going to be in the future in order to make some decisions today, right? So, and time series help us doing this. Another similar to the previous topics in econometrics, another reason of using time series is to estimate dynamic causal effects. So we spoke about kind of just causal effects. When x changes by 1 unit or 1%, y changes by beta, right? Percent or units or something. When we have time series, we want to estimate dynamic causal effects. For example, if the central bank increases the interest rate now, so you know, Russian central bank increased interest rate several weeks ago, like recently. So, like when the central bank does this, what will be the effect on the rates of inflation and unemployment in 3 months, in 12 months? So you see that we are not interested in the immediate effect, because usually there must be some channel how this interest rate spreads across the economy, and it takes some time to observe this effect. So if the interest rate is changed now, what is going to be the causal effect in the some future, in the near future? Or if the company increases dividend payout ratio, so for example, recently Lukoil and Nornickel introduced kind of large dividends. So and these dividends are kind of larger than before that anybody expected. So if the company does this now, what will be the effect on the stock price in 1 week, in 1 month? Again, so causal effect, but which is kind of lagged in time. Sometimes you don't have any choice. You have to work with time series. For example, rates of inflation, unemployment, stock prices, and many other variables just observed over time. So if you are talking about, well, if you go working for some corporate sector, and if you work in the firm, and if you are somehow in charge of predicting future revenue of a company, so revenue is also a time series. Because if you need to predict the future revenue, like make some forecasts, what will be if now we increase our prices, what will be if now we, I don't know, do some marketing campaign, whatever. So you don't have any choice. You have to work with time series. So that's why, and time series are around us. Um, so, and here is the major difference between what we are gonna talk about in the next lectures and what we have been talking about before. When we use regression models for the forecasting, this is something different from the estimation of causal effects. So before we were concerned in causal effects. If I do this, what is going to be the effect of this? And we've been trying to estimate this effect, to quantify this effect as precise as possible. We were concerned with immediate variable bias, we were concerned with the proper design of experiments, with the proper understanding of observational data, blah, blah, blah. So all of this was relevant. Now, for forecasting, R squared matters. So the larger is R squared, the better. An immediate variable bias is not a problem. We don't care about interpretation of the coefficients. So now, so probably for some of you, it is gonna be like good news. We don't care about interpretation of coefficients, and usually they are not interpretable. So betas and all the other coefficients that we are gonna estimate, they don't have any practical interpretation. They are just there. They somehow describe the whole model, but this is not our goal. So our goal is to build such model that performs good in forecasting. And good performance of the forecasting is possible when there is R squared, which is large. Well, usually not close to 1. We don't want such precision, but something like 60-70% is going to be okay. And external validity here is also important. So if we estimate the model using historical data, the same properties must hold in the near future, which is of utmost importance. So this is probably the most important thing for the whole time series understanding. If you take something from the past, and if you are trying to apply this for the future, you must be sure that past and future are comparable. They are similar in some sense. If not, your forecast is of no use. So it's just useless. So this is the most important difference from the previous part of this course. We are not concerned anymore with the immediate variable bias. We are not concerned anymore with the interpretation of coefficients. All we want to do is to build reasonable forecasts that match the future dynamics of the time series studied. So now, let's talk about some formal things in time series. So, a time series, sometimes it is called a stochastic process. So we denote this with these curly brackets, YT. So this is a collection of random variables which is sequentially ordered over time. So this is the most important characteristic of time series. Random variables are sequentially ordered over time. So what does this mean? if you observe ys and ys is observed before yt. So this is possible only if s is less than t. So I guess this is something natural. You cannot observe December before October. So this is logically impossible. So you have ordered structure. First goes October, then November, then December. Then the next year starts, January, February, etc. So Thursday cannot go before Tuesday. So first goes Tuesday, then Wednesday, then Thursday. So all the time, when we are talking about time series, we have to take this in mind. We have to keep this in mind, that there is a particular order of this series, and this order is kind of naturally inherited. And of course, it is important when you do some predictions, because you predict something next using something previous. So now, regarding the notation, a particular observation at the date t is going to be denoted with the lowercase yt. This is the same as we did in econometrics in statistics. So lowercase variable is the observation, and uppercase variable is the random variable itself. So capital T is the total number of observations. So when you have a time series, when you have like, I don't know, 80 quarters over 20 years, capital T is going to be 80, right? So if you collect the data for every day in the year, capital T is going to be 365 and so on. Now, yt minus 1 is going to be called the first lagged value, or the first lag. If you want to go back in the past by j steps, this is going to be jth lag, and it is going to be denoted with capital yt minus j. Right? So lag is important concept in time series. So this is the variable, the same variable, but observed one period before, or 2 periods before, or j periods before. Now, delta capital Y, this is the difference between the random variable observed at the period t and the random variable observed at period t minus 1. This is called the first difference in the variable yt. So these two are important concepts, and we are going to use them throughout the rest of the course. Oh, sorry, guys. Now, when we take logs of these random variables and take their difference, this is called the first difference of the logarithm of yt. Well, probably this is not that obvious why we are using this, but when we multiply this delta of logarithms by 100, there is going to be the approximate percentage change of a time series yt between periods t minus 1 and t. Remember, you had in your midterm some questions about interpretation of linear log, log linear, and log log models. So whenever your variable has a log transformation, immediately it has the following interpretation. So when there is a change in such logged variable, when you multiply this by 100, you get the percentage change of this variable. So this is, again, this is approximate percentage change. This is not the, of course, we know that the real percentage change is computed somehow differently. But now I will show you how we're doing this. So suppose that there is some stock price, for example, Tesla, and this is the data from the previous year. So it's October 21, 2022. So probably today the price is different. And then the next day the price changes. Look, if we compute the percentage change in a usual way, how we've been studied in school, then there is going to be this value, right? So we need to take the next value minus the previous value divided by the previous value multiplied by 100. Fine. If we take the log approximation of this change, we take the logarithm of this fraction. All this is going to be the difference in logarithms, or the first difference in logarithms. And we have approximately the same result, 4.5%. Not exactly the same, but this is approximation. And these approximations are useful because they are additive. So in the next lectures, you will see that we prefer such time series that are additive. So you cannot add these rates. They are not additive. But you can simply add these things. They're additive. So let me probably demonstrate you why we care about logarithms, why this is kind of interesting for us. So suppose you have like 3 dates. Date 1, date 2, date 3. Well, let's say date 4. Okay. And you observe some variable yt, and you have something like, I don't know, 14, 13, 16, 15. Okay. So now, if you compute this percentage change in a usual way, so this is gonna be what? So we skip this. So 13 minus 14 divided by 14 multiplied by 100. This percentage change. Now, if you take these logs, so we are gonna have something like this over this multiplied by 100. So you see that the values are not exactly the same, and the more the difference is between these values, the larger is the difference between these two approaches. But now look, suppose that I want to ask the following question. What is the rate of change between date 4 and date 1? Or vice versa, date 1 and date 4. So what should I do? In order to compute this, I need to take 15 minus 14 divided by 14 and have this. So this is the most correct way to compute the difference, the rate of change between date 1 and date 4. So now, if we sum these things, what we have? If we sum these things, what we have? So now, if I compute the same with logs, the result is going to be exactly the same. Look. So logs are additive. If I computed rates of change in logs between date 1, date 2, date 2, date 3, date 3, date 4, and then I sum all of them, the result matches the log return between date 1 and date 2, date 4, while these are not the same. So this is the reason why in many applications, when you work with time series, you will see the following definition of the rate of change. Instead of kind of the normal, the correct rate of change like this, you use the log approximation. So please remember, this is approximation. This is not a correct, this is not an exact way of computing rate of change. Of course, the most correct way is this. But it has a nice property. Whenever there are not large differences between the variables, log return is kind of near with the usual return, and the sum of these returns exactly matches the log return over the larger periods. This is an important thing to understand. Why do we use these logs? So this was some kind of introduction into the characteristics of time series. Again, observation, time span, first lag or Jade's lag, first difference of Jade's difference, and the log return, the approximation of the return of the variable. So now we switch to another concept. Remember, in statistics and econometrics, we used a very important concept of IID random sample. So it was the cornerstone of all our models. So we assumed that whenever we build some econometric linear regression model, panel data, whatever, so some variables are IID. Usually the error terms are IID, usually the sample is IID, and so on. So with this, we were able to introduce the following thing, so the following rule. So the information about the unknown distribution or parameters of distribution of x we could obtain from the sample on x. So we just take a random sample and we can characterize somehow the unknown parameters. And we are sure with this IID concept that the sample observations have the same distribution as the unknown random variable. So we assume that sample observations are mutually independent and they are identically distributed. The problem with time series is that observations are dependent. So the future usually depends on the past. And we are not able to collect an IID random sample in time series. So of course, if you consider the stock price, so let's just go and have a look at the stock exchange, Moscow Stock Exchange. Okay, so probably not the stocks, but let's see the currency exchange rates. So this is yuan to ruble, 12.61. It was yesterday, right? So what would you expect as the most probable value in the Monday? Of course, something close to this value, right? So you don't expect 0, you don't expect -10, you don't expect 100. You would expect something close to this value. Maybe slightly more, maybe slightly less, who knows. But still you will expect something this. So Monday and what you would observe on Monday depends on Friday, what you observed already on Friday. So this is a dependency in time series. And this is a huge problem because we are not able to apply the tools that we have discussed before. And yes, this dependency requires a different distributional theory, completely different than for cross-sectional observations. And we will kind of accurately take some parts of this theory, so we are not gonna discuss the whole distributional theory of time series, of course, but the most important concepts, the most relevant things we will discuss. And the most relevant things are following. So they are autocovariance, autocorrelation, and stationarity. So what is autocovariance and autocorrelation? So let's start with the reminder. So what is covariance and correlation per se? So if there are two random variables, x1 and x2, so this just comes from probability course, from statistics course. This is not relevant to time series yet. So there are two random variables, x1 and x2. They have means, mu1, mu2. And then covariance is defined as the expected value of the following expression. So you take random variable x1 minus its mean multiplied by random variable x2 minus x mean, and then you take the expectation of this. Correlation is defined as the fraction or ratio of the covariance and the product of standard deviations, sigma 1, sigma 2. So standard deviations of variables x1, x2. So correlation coefficient is always enclosed between -1 and 1. So this is the rule. So now, using this knowledge, remembering what are the correlations and covariances, we can build the concept of autocovariance and autocorrelation. So autocovariance is a covariance between a stochastic process at different points in time. So for example, we can define the lag h autocovariance as the following thing. So we denote this with gamma t at the period, at the date t, and h, which means h lags between the observation at t and observation at t minus h. Look, we are looking for the covariance between observation at the period t and period t minus h. And this is what? This is just an expectation of the following thing. Yt minus its expected value, yt minus h minus its expected value. When h is 0, then there is a covariance between yt and yt. And this is the variance of yt. Autocovariance between t and minus h lags and t h lags is going to be the same by symmetry. So this always holds. So here is an example. Suppose you have a stochastic process. So yt is constructed as the following thing. So for now, I am not talking about what kind of this stochastic process, so how it is called, why are we considering this. So all of this we are going to talk about in the next lecture that follows this one. So suppose that yt is constructed as this. So the sum of two random variables, IID variables, epsilon t plus epsilon t minus 1. 0.9 epsilon t minus 1. So there is something is taken from the past, multiplied by 0.9 plus something which happens currently. So expectation of epsilon t is 0, variance of epsilon t is sigma squared for all t. So now, what is the expectation of yt? So we compute this as usual. This is an expectation of the following expression. Expectation of epsilon t is 0. Expectation of 0.9 epsilon t minus 1 is also 0. So expectation of yt is 0. Expectation of yt minus h. Again, it is also 0 because expectation of epsilon t is 0 for all t, including t minus h, including t minus 1, including t minus h minus 1. Now, we are trying to compute the following expectation: yt minus expectation multiplied by yt minus h minus its expectation. So both expectations are 0. So we are looking for the expectation of the following product: yt times yt minus h. Okay, so we plug the expressions for yt here and for yt minus h here. So look, just an index changes. So the whole construction is the same, but at the t minus h moment, epsilon is t minus h here. So opening the brackets, we have the following thing. This is the expectation of epsilon t minus h. This is 0.9 epsilon t where is that? Yeah, 0.9 epsilon t minus h minus 1 here. Then there is 0.9 epsilon t minus 1 epsilon t minus h. And here this is 0.81, so the rest two terms, 0.81 at epsilon t minus 1 epsilon t minus h minus 1. So this is basically all that we can do for the autocovariance in yt and yt minus h. But now if we have some particular lags, for example, if h is 1, so if h is 1, we can plug everything here. And let's inspect what we see. Now, this is, of course, so here is the typo. This must be an expectation. This is not just this. This is expectation of the following expression. So expectation of the first term is 0. Expectation of the second term is 0. And here is a catch. Expectation of this term. So epsilon t minus 1, epsilon t minus 1. So this is going to be the variance of epsilon t minus 1, which is sigma squared. And this one is also 0. Well, finally, covariance between yt and yt minus 1 is 0.9 sigma squared. Well, as I told you, in this lecture and next lecture, we are going to do mostly mathematics and less empirical things and some fun in Python. So that's why let's, for a moment, get back to the statistics course. Now, autocorrelation. Autocorrelation is defined, well, in a similar way. We take lag h, and in the numerator we take covariance, autocovariance of lag h, and in the numerator we have the square root of the product of yt, variance yt, and variance yt minus h here. So autocorrelations, as the usual correlations, are always between -1 and 1. Again, lag minus h and lag h are equal by symmetry. And what we need to remember that autocovariance and autocorrelation are population characteristics. So they describe the population joint distribution of yt and yt minus h. And as you know, as you also had in your midterm, there was a question, what's the difference between population and sample characteristics? Because population characteristics are usually not known, right? When we work with the sample, when we work with the real data, with some observational data, population characteristics of the underlying process are not known. So that's going to be our task, how to estimate these characteristics together with the autocorrelation. Well, going back to our process. If we have this process yt, which is epsilon t plus 0.9 epsilon t minus 1, we know what is the variance of yt. This is going to be sigma squared. Variance of yt minus h is going to be also sigma squared. And finally, autocorrelation of the log h is going to be autocovariance of log h divided by the square root of sigma to the power of 4. So sigma squared times sigma squared. And for h equals 1, the autocorrelation, the first order autocorrelation is 0.9 sigma squared over sigma to the power of 4 under the square root, and this is going to be just 0.9. So this is going to be a number that does not depend on sigma. And you see that it somehow matches. So in the next lecture, we will talk about the properties of such processes and how the autocorrelations are constructed. So guys, any particular questions regarding the autocovariance and autocorrelation? So basically, with the help of autocovariance and autocorrelation, we are trying to answer the question, how the current value of the series depends on the past value of the series. So if I observe something today, does this depend on the past? If so, to what extent? The larger is the autocorrelation, the more is the dependency between current moment and the past. Questions? Okay. Now, the last important concept is the stationarity. When we spoke about cross-sectional econometrics, we treated observations as random draws from an underlying population, right? So it was always kind of number 2 assumption in any model. So the second assumption was this x and y, or y and x1, x2, x3, or some control variables as well. They are draws, random draws from the population, right? Now, we want to characterize the random variable yt by its distribution. And we want to characterize the collection of random variables yt, yt plus 1, yt plus h by the joint distribution. And of course, we know that important characteristics of the distributions are means, variances, and covariances. We called all these characteristics moments. The problem is that in reality, in practice, we have only one observation of a series. So all the time when you collect some history, this is one observation, the whole observation. You are not able to take another sample from the population. It is not possible, right? So whenever we spoke about cross-sectional data, we spoke, well, there is like gazillion of people. We can take a sample of 1,000 people and kind of record some characteristics. We can take another sample and record their characteristics. We can take the third sample and record the characteristics. And all the time, the samples are going to be different, hopefully. In time series, this doesn't work because you are not able to take different samples. If we observe this, the exchange rate, like yesterday, the exchange rate of yuan to ruble, this is one observation. The whole series is one observation. And you are not able to take another sample for yesterday. The history goes once, right? So this is the problem. We are trying to do something similar to what we know, but this is the obstacle, the first and serious obstacle. So only one time series sample is observed. how we can overcome this problem? We want to introduce some concept of constancy, right, or normality. Don't know, but normality not in the sense of normal distribution. So the most commonly assumed sort of constancy is stationarity. So why do we need this stationarity? In order to overcome the problem of one observation for the whole series. So we call time series strictly stationary. So this is usually a theoretical concept. So this never can be tested in reality. But again, the strict stationarity, if the joint distribution of the variable y between periods t1 to tk is identical to the distribution of shifted values, shifted by h. Look what happens. Well, let me show you. For example, we see some observations 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there is yt, which is like yt, y1, y2, y3, and so on. Right? So now we take the distribution of these variables, for example. So there is some joint distribution of these 5 variables. How do they compare to each other? Kind of joint mean, joint variance, and so on. So now we take these variables next. For example, we shift this like 3 periods before, or 3 periods in front here. And this distribution and this distribution must be identical. And for example, this distribution must be also identical. And for example, this distribution must be also identical. So any shift that you do should give you this set of the sequence of variables with the same, exactly the same joint distribution. So the strict stationarity requires that the joint distribution of this sequence of variables is invariant under time shift. So this is very strong condition. It is very difficult to verify empirically. I would say impossible to verify empirically. So you are not able to do that. And then we switch to the weak stationarity, which is usually tested practically, empirically, and that we are able to work with. So time series is weakly stationary, or sometimes it is called covariance stationary. If mean of yt and the covariance between yt and yt minus h are time invariant. So it means that it doesn't matter what is t, mean and covariance are the same. So yt is weakly stationary if the mean of time series doesn't change over time. So for each t, the mean of yt is the same, is constant, mu. The variance is finite, it doesn't change over time. So variance of yt is gamma 0. And this is finite. The autocovariance is finite, doesn't change over time, and depends only on h. It's not L, must be h. So the covariance depends only on h and doesn't change with t. So in practice, you can verify that there is a weak stationarity, for example, with the plot of the data. And the t values fluctuate with constant variation around a constant level. So let's go back to the slide where we introduced some plots of time series. Look, this left bottom series is not stationary. Why? Let's inspect these 20 years, 1960, 1980. So what is the expected value? How would we estimate the expected value? We would take the average. The average is going to be somewhere here, 3.3. So now we take this period of 20 years, 1990 to 2010. So what is the average here? The average here is somewhere about 4.5, 4.4 probably, right? So we see that this series is not stationary because the expected value changes. So what about this? If we concentrate on 20 years here, and we concentrate on 20 years here, so probably we see the same thing. So the expected value is different. What about this? Well, this is an interesting case because regarding the expected value, if we look at this year, 8 years from 90 to 98, and if we look at these 8 years from 2002 to 2010, so the expected value is the same, it's 0. But the variance changes. You see that variance here for these 4 years, so the spread of these deviations differs from, for example, these 4 years, right? Because this volatility was lower. So strictly speaking, neither of these time series is stationary that we inspected. But again, as usual, as anywhere that we study, we start with some benchmark. And this benchmark is the simplest possible form of series. And that's why we are talking about stationary, weakly stationary series. The next concept is the autocovariance and autocorrelation function. So for the covariance stationary processes, so when there is a weak stationarity, we can define two functions. So one function is the set of autocovariances for legs plus minus 1, plus minus 2, etc. is called the autocovariance function. So when for some series you build autocovariances for all sets of h plus minus 1, h plus minus 2, h plus minus 3, and so on. So this is going to be an autocovariance function, how autocovariance depends on h. An autocorrelation function is defined similarly. So this is the correlations, these are the correlations defined for every leg h, like this. There is also an additional concept of partial autocorrelation function. So, and in the third lecture, we will closely inspect autocorrelation functions and partial autocorrelation functions. So what's the difference? So partial autocorrelation function between yt and yt minus h measures the strength of the correlation between these values after controlling for the values between them. So what does this mean? Well, logically, yt can depend on yt minus 1. Yt minus 1 depends on yt minus 2. Yt minus 2 depends on yt minus 3, and so on. So, and in this way, when you compute the usual correlation, yt minus 3 is going to be correlated with yt through the set of variables between them. But if you exclude the effect, this kind of transition effect between variables, then you will see that there is no autocorrelation between yt minus h and yt at all. So all the autocorrelation just goes through the variables between them. So this is a nonlinear transformation of a autocorrelation function, and usually we denote this with alpha h. And these two functions are very important in model selection. When we select which model is the most appropriate model for working with the observational data. So each linear time series that we are going to talk about in the next lecture has a characteristic shape for each of these functions, and we will be talking about this in the next lecture.